Now we're going to proceed to understand the pH concept. pH is known as a logarithmic scale that is going to illustrate a numerical value for the concentration of H3O plus in a solution. This concept was actually developed by the observation of what happens when water molecules are present in pure water. It turns out that water molecules are in an equilibrium reaction. Water molecules go through the process of autoionization. This process states that water molecules are going to attack each other. And one water molecule will act as an acid, meaning that is going to donate an H plus, while the other water molecule is going to act as a base and receive that H plus. In turn, from this reaction, we form hydronium ion and hydroxide. So even though this reaction has forward and reverse rates, understand that the preferred form for the reaction is water molecules by themselves. Now, from these studies, it was understood that when reactions are, or sorry, when autoionization happens in water, we consider water to be neutral because overall we see that the concentrations of hydroxide and hydronium are the same. Later, it was demonstrated that if you have substances in which now the different substances for hydronium and hydroxide vary in concentrations, then we consider them either acidic or basic solutions. So, in a solution that all of a sudden you can form a higher concentration of hydronium compared to hydroxide, that is considered an acidic solution. While if you have a substance in which the hydroxide concentration is higher compared to the hydronium concentration, then that is considered a basic solution. Overall, when we have an acidic solution, this is going to be a solution, as I just mentioned, that specifically the hydronium concentration is going to be higher than the one of hydroxide. When it comes to this logarithmic scale called pH, that means that the value of pH is going to be less than 7. On the other hand, if we have a solution that is called a basic solution, in this, we're going to find a higher concentration of hydroxide compared to the concentration of hydronium. But when it comes to the pH scale, let's understand that solutions that are considered basic, or in other words, alkaline, are going to have a pH that is greater than 7. Neutral solutions are going to have equal concentrations of hydronium and hydroxide, so the pH is exactly at 7. Many substances that we are exposed to in everyday life, you can see that they can involve detergents that we have in our households or even foods that we consume are going to have different values of pH on this scale. And based on those pH values, we can consider them acidic, neutral, or basic. pH can be measured with a variety of instruments. We can see in letter A that this is called a pH meter. And a pH meter is going to be an instrument that over here, the electrode is going to be submerged in a solution. And then in the screen, it tells you specifically what is going to be the pH of the liquid. In this case, since we observe that the screen is saying that the pH is 4.00, this substance is known to be acidic. Another way that we can detect the pH of a substance is by using pH paper. pH paper, it's similar to litmus paper in the sense that it's going to change color, but pH paper actually has more of a scale that can be attached to digits within the pH unit. So even though there's color changes, we can actually use these color changes and then we look at the specific guide that we have on the pH paper that we purchase, and depending on the color that the pH paper turns once it's submerged into a substance, we can determine the pH of a solution. Lastly, understand that nature also has pH indicators. So, for example, purple cabbage has a plant pigment that is called anthocyanin. And anthocyanin is actually known to change color depending on the exposure to different concentrations of hydronium or hydroxide. We can observe on the test tubes that we have in the test tube rack all the different colors that the purple cabbage can turn into when detected pH. The low pH are going to be in this fuchsia light pink range. Typically, when it is in the blues or almost light purple, that's going to be pH 7. Anywhere that is green to yellow, that's going to be basic pHs. When it comes to pH, let's understand that there's going to be mathematical equations that we can utilize in order to calculate the pH of a solution. We can see that the basic equation of pH is the following. pH is going to equal the negative log base 10 of the concentration of hydronium in a solution. Understand that the concentration of hydronium is the same thing as the concentration of protons because hydronium in essence is a source of protons. So using concentration of hydronium or concentration of H plus, in other words, protons, is the same thing. Since this equation is a logarithmic base 10, if we raise everything to the power 10, then this equation can lead us to an equation in which if we are given pH, then we can calculate the concentration of H3O plus in a solution. And you can see in figure 7.21 how these two equations can be utilized. So if you are given H3O plus and you're trying to find pH, this is the equation that you use. But if you're given pH and you need to find H3O plus, you can observe that to go from here to here, we are going to use this equation. But since we know that in these solutions we may have OH, how do we relate hydronium to hydroxide? We can observe that if you need to find concentration of hydroxide from hydronium, this is the equation that we utilize, where concentration of hydroxide, knowing that you know the concentration of hydronium, you're going to do 1 times 10 to the negative 14 divided by the concentration of H3O plus. It tells you what's the concentration of OH minus. But on the other hand, if you have the concentration of hydroxide and you're trying to find the concentration of hydronium, this is the equation that we utilize. Establishing that since you know the concentration of hydroxide, all you have to do is 1 times 10 to the negative 14 divided by the concentration of OH minus is what gives you the concentration of H3O plus. Let's do some examples to practice how to utilize these equations specifically in problems. Here, you only have specifically just an illustration of the relationship between hydronium and hydroxide and some of the household products that I mentioned before. Let's actually do some calculation examples. For these practice problems, We are given certain values and we are going to first classify, given the information, if these solutions are going to be acidic, basic, or neutral. In order to do this, we must calculate pH. So in letter A, since I am given H3O plus, I can calculate pH directly. I can say pH is going to equal negative log of 1.0 times 10 to the negative 5 molar. When I put this in my calculator, I see that the answer is going to be specifically 5. Now, there are sig fig rules when it comes to doing pH. If we go specifically from concentration to finding pH, notice that what happens in terms of the sig fig rules is that since this value has two significant figures, then the pH needs to be written specifically with two decimal places. And that's the rule for sig figs. When you have, in particular, given the concentration of hydronium and you need to write the pH. Let's now do problem B, in which I am given OH minus and I need to find pH. In this example, oh, one last thing. A pH of 5.0, that means that the substance is acidic. Now I can move on to letter B. In letter B, I have a concentration for hydroxide. So since I have the concentration for hydroxide, but I'm trying to find pH, notice that my flow of work is that first I'm going to utilize this equation to find H3O plus. Once I have H3O plus, since I'm trying to find pH, then I'm going to use this equation. Says let's use those two equations to find pH. At first, I'm going to try to find H3O plus concentration. So I'm going to do 1 times 10 to the negative 14 molar and divide it. Let me actually write the 1.0. And I'm going to divide that by 1.0 times 10 to the negative 6 molar. When I put that in my calculator, I find that my result is 1.0 times 10 to the negative 8. Now that I have this, then I'm going to use the pH equation. pH equals negative log of the concentration of 1.0 times 10 to the negative 8 molar. And when I plug this in the calculator, I'm going to find that the value is 8. But again, when it comes to this, since my original concentration had two significant figures, the correct answer in terms of sig figs is going to be 8.00. Because if my concentration has two sig figs, then my pH must have two decimal places. When we have a solution of pH 8.00, that means that my solution is basic. Let's now move on to the other example that we have on the slide. It reads, cow's milk is slightly acidic, meaning pH of 6.5 to 6.7. We're going to calculate the pH of the following beverages. Similar to what we did in the first part, for non-dairy milks like rice, soy, almond, we can utilize directly the pH equals negative log of H3O plus to find the result. So if we do letter A, we're going to say, well, pH equals negative log of the concentration given, which is 1 times 10 to the negative 6 molar. When I plug this into my calculator, I see that my answer is 6. But because there is one significant figure in my concentration, that means that I need one decimal place in my answer. So the final answer is 6.0. Let's now look at orange juice, which has a hydroxide concentration of 1 times 10 to the negative 10. This example, similar to letter B, what we're going to do is first find hydronium concentration. H3O plus equals 1.0 times 10 to the negative 14 molar divided by 1 times 10 to the negative 10 molar, which means that this is going to equal 1 times 10 to the negative 4 molar. This value is then placed in the pH equation. pH equals negative log of 1 times 10 to the negative 4 molar. This equals the value of 4, but because my original concentration had 1 sig fig, I need to put one decimal place in my final answer. So the correct answer with the correct number of sig figs is going to be 4.0. So we can observe that non-dairy milks or orange juice are both acidic solutions.